let's get started. First of all, welcome back. We have a much smaller class now, 45 students. First, I will go over the homework 1 and 2. Actually, I'm only going to talk about one issue there. Several people asked me a very good question. They asked me why, when they use the object down, they say instructions after the return. So here's a return instruction. So this is a example of the add function. This is 32-bit. Oh, this is actually 64-bit because RSI there. So this is 64-bit. So if you look at this function, there are don't worry about the first instruction. It's related to security, but it's beyond what we're going to discuss in this class. So the second instruction is basically move something, then there is just a return. After return, the control flow obviously should go to somewhere else. So why there is an instruction after return? That really makes sense, right? So this is a very good question. It can be very deep. It's a very deep question. So this one, in short, this one is not really a valid instruction. The CPU is not supposed to execute. That's a very short version of it. Then why the tool we're using is interpret it as an instruction. It's because there are basically two algorithms to disassemble instructions. One algorithm is called a linear disassembly, and this is an algorithm our tool object found use. So this algorithm is very simple. Basically, it just iterates through all the code segments in a binary. Whenever it sees some bytes, it tries to interpret it into instructions. So it doesn't really consider the control flow. So it's not trying to understand what this instruction is doing, because all of those disassemblies is actually static disassembly. So the tool object down, this is a executable. This is a process. This process is running. But whatever we're disassembling here, that piece of code is not running. Okay. So object down, we're just say the first 4 bytes is one instruction, the next 4 bytes another. Then say return. After return, we'll just keep a disassemble. That's why we're disassemble this as a valid instruction. But it doesn't mean the CPU will execute that. So if you use another tool, I recommended you to use in this class, which is Battery Ninja or actually IDA-Pro, Battery Ninja, or even the other one. So all those tools are more advanced than object down. So they use more complicated algorithms. At least their algorithms are based on something called recursive disassembly. So in that algorithm, it will consider the control flow. So when it disassemble everything, you also try to reason the control flow there. When you say there's a return, it knows it's not going to go to the control flow is not going to the next bytes, right? So if you use the Battery Ninja, this is a screenshot I took from the Battery Ninja online version. As you can see, Battery Ninja will say those are just the bytes. Okay, just them. We're not interpreting it as instructions. So both algorithms, they have their own advantages and disadvantages, and there are a lot of binary tricks to trick those tools, disassemblers, to generate wrong instructions, interpretations. That's one of the defense techniques in a lot of softwares. So I think that's the only thing I want to discuss in homework 1 and 2. So if you have any other questions for homework 2, you can go to my office hour or the TA's office hour. So next class,
we talked about some background knowledge for this class. We talked about compilers, linkers, loaders. We talked about x86 and 64 architecture. Some of the instructions, their general registers, Linux, file permissions, set UID programs, memory maps, system calls. And in this class, we will keep talking about the background knowledge, and we will start talking about buffer overflow attacks, depending on how much time we have. So first, we will go over the basic knowledge of ELF files. We'll talk about the headers, section headers, and what is lazy binding, and how Linux and ELF files use lazy binding. And also talk about program headers. We will also start talking about stack-based buffer overflow. This is the oldest form of software hacking, stack-based buffer overflow. Some literature call it sequential buffer overflow. So this is a little different from heap-based buffer overflow. We will talk about the history of it. We will look at how the information C functions need to run, several C calling conventions. Then we'll check how to overrun local variables. Today, we probably don't have time to talk about how to overflow return address. And we will spend maybe more than one session on that. So we will see a lot of approaches to overflow return address and put share code at different places in the address space and take control of the computer. So ELF stands for executable and linkable format. This is the standard executable binary format for Linux. You have been seeing different files using different extensions, but all of them are just ELF files. There are bin files, binary files, O, object files, KO, kernel object, and so we share the memory, share the object files, and .A for libraries, AXF probably for embedded systems, and ELF files contains programs and also its data, code and data, and it also has a lot of meta information to describe how the program should be loaded into the memory, how the program should be executed. And obviously, it's critical for security. So we're going to work with ELF files throughout this semester. And this is actually a big topic, but we don't have to understand everything, every bit of it. You just need to remember several simple things, and that will help you get through the semester. An ELF file basically has 4 types of components, as this figure shows. The first one is its header. The header is called the executable header. Then probably the most important part is sections. Sections, there are many of those sections. So sections are where the code and data actually stored in this file format. And each section, there is a corresponding section header. This is a well-defined data structure. And those sections and section headers, they give the linker view of the program. Then at runtime, the program, after this file is loaded into memory for execution, the OS actually will look for the program headers. You can see every section has a section header, but there is no such thing called program to map to program headers. Programs they map to some program headers, they map to something called segments. And a segment is what the OS views the process. And segments are basically just a bunch of sections bundled together. Okay, so those are just the four major components you need to remember for ELF file. The header, the program header, sections, and section headers. That's it. So here is the data structure for the executable header, which is the beginning of a binary ELF file. Obviously, you won't have to remember all of this. So when you need to understand some of this, just Google it. But we will look at several important fields to give you a feeling what information is stored here. As you can see that the first 16 bytes is unsigned chunk, and it is used to store magic numbers. And for ELF files, the first 4 bytes are always determined. It's just 7F in X and the ASCII ELF. That's determined. If this is a valid ELF file, it should always have those 4 bytes. After that, there are still 12 bytes to store other information. Then there is 2 bytes unsigned. So the second one, unsigned integer 16 bits, that's 2 bytes. So those 2 bytes are used to store the type of the file. There are several different types of ELF files. The first one is executable, a program you can run. Usually, that's for classic programs, static link. Then there are shared object, dynamic libraries. Then there is another 2 bytes to show what architecture this file is for. Some computer ones you will see are x86. Then there are just other information. So those information actually is very easy to guess the meaning of this. Example here, this one is called entry. So that is the program entry point of this file. But when you program in C, you start with the main function. But the main function is not really the entry point for the binary. The entry point is probably underscore star, probably that function. But that function eventually will call your main function. So the entry here, actually points to that. Then this one, PH of this is a program header offset. This one, SH, section header offset. So basically it tells you in this file, where are the program headers, where are the program headers, where are the section headers, and for each section, where each section header, we can know where is the corresponding section. Okay. And this is obviously a static view. We're talking about files. We're not talking about process. And there is a tool for us to analyze ELF files. This read ELF tool can help us do that. So I will show you how to do that. So I'm going to use that simple code we used last week, 2 weeks ago, and so if we just do read ELF, show the headers, and this is a 32-bit version, it will show us the magic code is 7F, then ELF. So this is a 32-bit file. The OS is the and the machine is for Intel machine. And even though this one is just but the GCC actually compiles to the dynamic object file. Okay, that's a new version because this is dynamically linked. If you do this on other programs like just LS, you will get the same result. Shared object file. But if you compile this, and link this statically, you will get here. You will not get dynamic object file. Instead, you will get dynamic executable. So this is how you use a red ELF file. Actually, you can do a lot of other things. Yeah, it can do many things. You can use it to read the other sections as well. Let's see. Also, both this type of debug information for ELF files. We're not going to cover that in our class. As you can see that we can do file headers, program headers, section headers, even symbols. So use this tool, you can read ELF files. So next we will talk about the sections. Sections are where code and all kinds of data are stored. Because there are so many different types of data you can store in a file, there is no standard saying this section, what should be the structure, what should be the format. Imagine there's code, then you just put code there. If it's just some resources like an image, you can put a image embedded in there. So there's no standard format for that. And we divide those data logically into those chunks, and we call them sections. So sections are actually used by the linker to link different object files together and also load into the memory. We will look at several important sections. So the section header also, each section header follows this format. First, it has a section name, then section type, section flags. As you can see, we have several examples here. The name usually starts with a dot data, dot ro data, dot text. Type can be, let's say, program bits. So this is a type of program bit, which means that section stores binary code, machine instructions. And there is a symbol table type, means that section stores those symbol tables, so probably a lot of strings. And this one is like a string table. This is the relocation, dynamic symbols. Besides types, there is also a flag field. Tells you if that section should be writable or executable in the memory. So there is a field called the write. Also, we'll have this allocate. This one means this section should, when the program is loaded into memory, so this section should be loaded to memory. Because when you load a binary to memory, you do not necessarily load everything. Allocate means this section should be loaded. So we can use the tool with ELF to check this out. So this is the same and binary 32-bit, and we use read ELF hyphen uppercase S to get all the section headers.
As you can see that this program has 31 section headers, and some of them you're probably already familiar with. For example, there is so all the names start with a dot. That's just a convention there. If you design your own Pyro program, you don't necessarily follow that rule. But here you can see this dot text. That is where you store the program. That's why the type is program bits, means it's machine code. And obviously the permission for it is A and X. X means this is executable. A means this section should be loaded into memory. But there is no W there, right? So this section should not be writable when the program is running. There are a lot of other sections we have on our machine code. For example, the init. This is obviously some functions for utilization of this process, and those functions are not really created by you. Compiler will inject those functions when you develop the C program. When you develop C, you just write your main function and other functions, and they were all those functions you develop. They will go to the about text section, and init will have utilization functions, and obviously correspondingly we have the fill section. So then we have read-only data. So read-only data obviously it's not executable, so we don't have X here. We don't have A. Then we have EXS for global variables that are not initialized. And since they are global variables and they're not initialized during the program running, those variables value will be changed, right? So this section has to be right. That's why it has W. We have a lot of other sections. We will talk about several very important ones soon. One is the PRT, program linkage table, and the GOT global offset table. There have been some attacks utilizing those two sections. That's why I'm going to talk about those. Three important flags to remember the meaning. One is write, means that section is writable. Alloc means those contents should be loaded into virtual memory, and execute instructions means that section has executable instructions. So those sections we already talked about. Next, we will talk about that a very important feature called lazy binding. So when you compile your own C program, you may have several different C files. So each of those C files will be compiled into its own object file. But when you program in one C file, you may call function in another C file, right? So at runtime, that when you call that function, you need to know the address of that function, even though it's in a different object file. And it is a linker's job to build those connections. And that step is called often called linking or binding. There are static linking and binding, which means when you compile this program and link them together, you have one big binary, and that binary on rest on your file system already solved all those address issues. So all those addresses, references, they have been resolved. However, in model OS, we use these shared libraries. For example, you develop a program, your friend also develop a program,
both those programs run on the same machine, and both programs use the standard C library, libc. So to save space, the operating system will only have one C library in the physical memory. So that C library is virtually mapped to both process. One is your program, another is the referred program. But there is actually one physical copy in that memory. So at compile time, there is no way for your program to know what are the addresses in the libc library. This can only be done at load time or after load time. So that's why a standard approach is called a binding at load time. This is for shared libraries. So when a binary is loaded into a process, the dynamic linker, which is part of the loader, will resolve the references to functions, global variables located in those shared libraries. And those addresses actually they are not known at compile time. This is the idea of binding at load time. However, there is also a problem with this approach. Imagine you develop a program, you will call several C library functions. But there are so many C library functions. There are thousands of those, right? So if the loader will resolve the references at load time, it actually wastes a lot of time and CPU cycles to do that. Because your program may not really use all of those functions. So another approach in reality, right now all the OS are doing, is called lazy binding. So basically the idea is when the loader loads a binary into a process, the loader will not resolve those addresses. The addresses will only be resolved when that function, a particular function, is called. It's called the lazy or late binding because the resolving those references, they were deferred until the first time you actually use it. So by doing this, the advantage is you save a lot of CPU cycles. You do not waste it to resolve things you don't need to resolve. Also, there are disadvantages. For example, the first time you call it and the second time call it will cause different CPU cycles. The first time you call it will be much slower because the first time you call library function will be much slower because you have to resolve the address, right? Of course, this is behind the scene. The loader will do the job, but it will be much slower. For some of the systems like real-time systems, this is not acceptable. Real-time systems require everything should be finished in a determined time. But in general, this is a very good feature. So in Linux and also ELF, so this feature is implemented with the help of two sections. One is called procedure linkage table. Even though this section is called a table, everything inside this table is actually instructions. So this section is actually machine code. Then there is a global offset table. That one is actually addresses. So PRT is the code section. It has stubs of all other library functions. And the GOT or GOT PRT is a data section that has those addresses. We are going to use one example to demonstrate how it works. Let me see. So I write a very simple program, and we can see how this lazy binding works for that program. Okay, this is my lazy binding program. As you can see, this program is not doing anything fancy. We were just to pull printf twice. And printf is a leap-say function. It's not doing anything else. This program is dynamically linked with leap-say. So when you compile this, it doesn't really know where the address of printf. So we're going to use GDB to debug this program, and you will clearly see that the second time and the first time you call this function, the program actually behaves differently. This is the first time we use GDB in class, and we're going to use a lot of GDB in this class. So in the virtual machine I gave you, I installed several plugins for GDB to make your life much easier. So some of you probably used the GDB before. GDB is powerful, however, the UI is terrible. We do not see the registers by default. We do not see the memory by default. So I put several plugins there, and those plugins I use by hackers to make it easy to use.
So what we can do is we use GDB lazy, this one. So this is this. So we can. So if we just run this program, it will just finish running, and it will print out the first call and the second call. It doesn't give you anything. What we're going to do is we are going to. By the way, if we just run this program, here you will get the same thing, just the two printouts. So we use GDB, then we debug this lazy file. So first we set a breakpoint to the main function. That's how you set up a breakpoint. Address the function main, yes. So we just do a b main, then we set a breakpoint. Then we just run this program. We use R or run, they're the same. We run this program. Now this program is running, and it hit the breakpoint at the first instruction main. Okay, so this is the first instruction main, the main function. We hit the breakpoint here. As you can see, the plugin I installed give you all the register information there. So all the registers. You can also see stack here. Oh yeah, this is actually a stack. I'm not sure which direction this is going. Okay, so this is low address. This is a high address. So this is a different from how usual idle stack. Usually a idle stack I will draw high address here, low address here. So this is the opposite. But you can see that this is a stack, current stack. This is a code, a binary code, and there's other registers. So now I'm going to execute several instructions. To do that, I'm going to use the command ni, means next instruction. So when I do next instruction, I first execute that underground 32 instruction. Now I'm at this instruction. We're not interested in those actually, so we keep going until we see the function for the first time. This is the first time we're calling the function printf. So printf actually eventually leads to this thing. So this is printf. So we're going to call the function printf for this first time. But printf is not part of my function, right? It's part of a C library, deep C. That's why we are actually calling this address, which is the PLT, program linkage table. So we want to get into that. So we're, instead of doing ni, we'll do si here, means step instruction. So by doing this, we will go into the function, and you can say now we are actually at the section of PLT.
Okay. So we do one more step. So there is a jump. It will bring us to some other place. So right now it is not resolved. It actually will bring us to another function. You can see there is another function, which is quite complicated. So if we keep doing, it will bring us into other functions and eventually bring us to a library function.
So this is obviously a library function. But this library function is not the puts library function.
It is actually part of the loader that is going to resolve the address of puts or printf for us. So we can jump out of that using finish. So now we do finish, we get out.
Now we're back to our program. So this is the first call. This is the second call. Okay. So right now, that address is the address of puts is already resolved. So if we
Keep doing this, get into the second call, you will see the second call will be different from the first call. The second call, we went to the library, the linker library to resolve that. The first call. The second call, the beginning is the same, but this instruction will be different.
So before we will execute this instruction, so what is the meaning of this? So this is somewhere in the memory, there are 4 bytes indicate where should I go. And previously that 4 bytes is the functional address to resolve other functions, mixing functions. But right now this function address is already that
Area, that's 4 bytes, are updated to the function of the address of puts. So if we execute here, we will
directly jump into puts. See, now we're in puts. So you can see
we called the same function twice, but actually the underlying mechanism there are different. So this is how the lazy binding works. Any questions here? Yeah, I know this part is a little bit hard to understand, but this will be part of your homework. So you are going to debug this step by step and understand what's going on here. Also, I will send you some reading materials to explain to you everything here. Okay, let's keep moving. So we're going to use a lot of GDB in this class. So I also give you a link of GDB cheat sheets there. So get familiar with this tool. So like I mentioned before, the ELF file actually provides us 2 different views of a program. One is called the section view. Another is called the segment view. In short, you just need to remember segments. There are a bunch of sections bundled together. Okay, and we can use tools like read ELF to read the program headers and also which corresponds to the segments. So for any segments, also there are types, whether they are executable, writable, and readable, or there are some flags saying this is dynamic or just for linkers. So here is another example of the same and binary. We use read ELF hyphen lowercase l, and you can see that there are not so many sections. There are not so many segments anymore. So here we have all the sections, and those sections they are grouped together into segments. For example, where's the number here? I do not say segment number. Those sections that are grouped together. For example, all the code sections you need
txt, they are grouped together into segments. And here we can see different program headers with different flags, read, write, and execute. For example, this one looks like this one is acceptable. So this one probably maps to this segment. Let's keep going. Okay, that's all I want to talk about ELF files. There will be several homework on ELF files to help you better understand what's going on. Okay, so next we are going to dive into real hacking. So the first one we talk about is stack-based buffer overflow. This is classic. So the objective for this one is to you will understand how stack works for x86 and also 64-bit machines. We do not cover other architectures, for example, ARM, RISC-V, or MIPS. But if you understand how stack works for these architectures, it will be easy for you to apply knowledge to other architectures. They are very similar anyway. You will be able to identify buffer overflows in your program. Basically, I'm saying identify simple buffer overflows. So this can be very, very tricky. Sometimes the program can be very complicated. You cannot identify the buffer overflow. Well, in general, this problem is undecidable. If you took theory of computation class before, you know that it's not possible to identify all the bugs in the program. This is an undecidable problem. Also, you will learn how to exploit a buffer overflow vulnerabilities. A little bit history of buffer overflow. So stack-based buffer overflow was discovered back in the 80s. But right now, it's just not possible to tell who discovered this type of vulnerability first. Not possible anymore. Actually, this vulnerability played an important role in the first felony conviction in US under some act back in the 1988. So I guess some of you heard this Morris one before. So Robert Morris, he was a student at Cornell University back in the 80s. And he developed this infamous worm, Morris worm, and that worm took down a significant part of the internet back in 1980s. And that worm utilized several buffer overflow bugs in a server program. I don't remember what server program it is. Probably it's an FTP server program. So we mainly use the buffer overflow stack as a buffer overflow. But that was back in the 80s. So if you follow computer science research, Robert Morris, right now he's a professor at MIT. He's an HM fellow. He has several startups, very successful startups. Also, you know there's a computer called Y computer or something, like an investment company. So he's part of that as well. So he is this very successful computer scientist and also entrepreneur. But before all that, he created this work. However, here back in the 80s, not many people know how to do buffer overflow. There was no good articles, teaching materials
teaching people how to do this. Until 1996. So this article, Smashing the Stack for Fun and Profit. So this article was published in an online hacking magazine called Crack. So this magazine still exists. Right now, they still publish articles, but it's just not that influential anymore. But still, hackers, they are very proud if they publish here. So this is the first well-written article on how do you do a stack-based buffer overflow. So this is a classic. Everyone should read this one as homework. It's not actually very easy to follow. It has several pages, and right now it's very difficult to replicate those environments anymore. But you can get a basic idea how it works. So the author of this article is obviously a student of one. Okay, but if you just Google, you can find who is actually behind this student. It's not like Bitcoin. You cannot find who invented that. So buffer overflow, even today, is still a very serious problem. This is a screenshot I took from MITRE website, and here we have top 25 vulnerabilities, and buffer overflow is still ranked number 1. Even though we have so many mechanisms to defeat buffer overflow, the software layer and system layer, so many techniques to do that. Well, we'll talk about a lot of those techniques in this class. But still, it's a serious problem. And actually, in this list, you can say a lot of other vulnerabilities we will talk about. For example, use after 3, integer overflow. Those are also vulnerabilities we can use at binary level. So especially use after 3, and when it's specific to heap security. Null pointer reference, this is also security. We can also see a lot of vulnerabilities like cross-site request forgery, maybe cross-site scripting. So those are classic web security vulnerabilities, which we will not discuss in this class. I probably said this before. I think web security deserves its own class because it's such a big area. The browser is kind of like an operating system. And on top of the browser, you run all kinds of programs, JavaScript, even binary code, you can run directly inside the browser. So in this class, we focus on the binary problems. And so all of you are C programmers. So for a C program to run, it needs this following information at runtime. Obviously, it has code parameters for different functions. Functions will return values, and there will be global variables shared by different functions. There will be local variables. There will be some temporal variables. There will be a lot of address or even return address of the function that called the current function. And there are function frame pointers and previous functions frame pointers. So when you program at the C level, you do not really think about where those things are stored. You don't think about that. It is not the software developer's job to do that. Even though C is very low level, you can do whatever you want. But here, don't think about that. It is the compilers, developers, and also OS developers' job to actually map your C code to the memory, the virtual memory at least. Okay, but in this class we're doing hacking, so that's why you have to understand how it works at the lower level, lower at the SQL level. So let me remind you what are local and local variables. So local variables are those variables you declare inside a function. So they can only be accessed by statements, say statements, also in that function. And the local variables are not supposed to be known by other functions. However, global variables are defined outside a function, and they hold their values throughout the lifetime of your program, and they can be accessed by any function defined by that program. Also, we have those arguments or parameters. When you call a function, we will pass some arguments, and those arguments usually the way we store them are very similar to ways we handle local variables. So here we have a simple program called global and local variable program. This program has one main function and one func. There's two functions. So the main function, we have two local variables, one initialized, one uninitialized. Then we just print out the global variables. So there are two global variables as well. Actually, both global variables are just pointers. The first one points to a string. That string itself will be stored in read-only data, and there are the global variable g_I will point to that string. Then there is another global variable g_U which is not initialized. And that variable probably will go to the BSS section. Then we have the func, which takes one parameter for d. Then it has two local variables. In this function, we just print out the address of those three local variables. I also call the argument the local variable. So we print out the address of I, U, and P. The main function, we will print out the address of the two global variables, and also two local variables of main, and also we will call the function with the argument 10. So let's take a look at, let's run this program, 64-bit version and 32-bit version. Let's see the address of those variables. So this is a 32-bit version of this program. So we can see the global variable at the address starting with 56 something, two different global variables. And the local variable we have main, we have the func, and the main local variables is at ff something. The func is also at ff. Also the third one p is also at ff. So actually ff is at the top of the memory space, right? So 32-bit address space is 4 GB, which can be represented by this 4 bytes. So the top of the physical or virtual memory address here is actually OF. 0x, OF, 8F. That's the top of the memory, right? So this is close to it. This is very close to it. Okay. At the top of the memory space, in your first homework, you will know that stack is it. So this is where the local variables, we put them on stack. And the global variables are not on stack. If we look at the 64-bit version, things are actually similar. The global variables are somewhere in the middle. The local variables, they are also quite tall. Actually, the reason we're not in FF instead of 7F is several reasons. For 32-bit version machines, we're not actually using all 64 bits. Sorry, we're actually not using all 64 bits address. We're not using that bit memory address. So this is also close to the top. So this is where stack is. And another thing we can do is we can use the tool NM to list the symbols in the program. And you will see something interesting here. Okay, so now we are listing the symbols of this program. And left-hand side, we have the address of the symbols. Okay, we can find interesting symbols like start, which is the entry point for this program. We can have the main function address. This is actually offset. So this is where your main function is. Also, the type here indicates key uppercase means this is an external text. If it's lowercase, I believe it means it's internal text, should not be called like others. Then there are B means Dana, B probably BSS. Oh yeah, B is definitely Dana, B is definitely BSS. Remember, this one is initialized. Yes, that's why it's in Dana. This one is uninitialized, that's why it's in BSS. So we can find G underscore U, G underscore I, but do you find the local variables? We have 4 local variables. We have L underscore I, L underscore U. What else we have? Oh yeah, we have 2 of those. The main function has a local variable with the same name. Those 4 local variables, they have actually the same name. Okay? But they are local to this function. That's why when you see the symbols of the program, they do not exist. They're not global symbols. Outside, after the program is compiled, we lose that information. It's not here. Okay. You cannot find those here. So to call a function at runtime, what we need is we need the function code. We need the argument for that function. And in 32 dimensions, we use the stack to store those arguments, parameters. And in 64-bit, we actually use registers. We will talk about that later. The return addresses of function, they are actually stored in ELX or RAX. Global variables, we go to BSS or data section. Local variables, most of them will be on stack. Some of them will be directly stored on registers. Obviously, if you store things in registers, things will be much faster. But you only have so many registers. So you have to use the main memory, and you will use stack part of the memory to do that. Temporal variables, same thing. The return addresses, we will also store that on stack. This is true for x86 and also 64-bit. For ARM, it's a little bit different. ARM, there is a special register you can use to store the return address. But you only have one register. So if you call that function, if you call several functions, still that address has to be stored into memory. But they do have a register to do that. Then there is a function frame pointers.
it's either EBP or RBP. So BP means, I think B stands for base pointer. Now SP is obviously stack pointer. Then the E, just to say this is a 32-bit, R say this is 64-bit. So stack is used in all architectures. In most architectures, the stack goes from high address to low address, goes down. But to some architecture, you can do either way. For example, ARM, you can make the stack go up. But most people are still, when they design a system OS or whatever, they still make the stack go from high address to low address. And the functions, they can push registers values onto stack, and they can also pop values from stack into registers. There are several architectural support features on x86 and 64 to support stack. First one is the stack pointer register, ESP and ISP. Like I said, SP means stack pointer. So this register should always hold the address of the top of the stack. Okay, remember the stack goes from high address to low address. So where is the top of the stack? Low address is the top of the stack. Where you start is the bottom of the stack. Okay, so we have a push instruction. For example, we can push ELX or push RX. So this instruction will decrement the stack pointer. So this instruction has two steps. The first step is to decrement the stack pointer, which is the ESP or ISP. Then it stores the value in ELX to the memory location pointed by the stack pointer. So this instruction will not change ELX or IX, but it will change what the memory were pointed by the SP. Then we have another instruction pop. Pop will first move the value at where the ESP points to the register, then increment the stack pointer. I have some animations to show that later. So besides push and pop, there are several other instructions to affect the stack. Call is one of them, return another one, enter and leave is actually kind of like a shortcut to group several instructions together. Next, we will take a look at those instructions closer. So let's say we have a push instruction, and the value we want to push is in register ELX. So the argument for this instruction doesn't have to be a register. It can be just a number. Okay. Let's say this is a stack. This is a high address. This is low address. So the stack goes this way. Right now, the ESP, obviously this can be extended to 64-bit version. Everything will be the same, except for the size of the registers and also the size of the data. So here, usually everything is 4 bytes. For 64 bits, obviously just 8 bytes. So ESP points to this value X on stack. Now we're going to execute push ELX. So the value of ELX, the value inside ELX will be stored here. Then also ESP will be updated. ESP will point to here. So this is push. Then pop, similar. This is the opposite operation. So pop will pop whatever ESP points to into the register ELX in this case. So obviously, for pop instruction, the arguments you cannot have a immediate number. You cannot say pop what, if that makes sense. But you have to pop it into some register to store. So in this case, ESP points to the value X. After pop, the ESP were increment actually, and we were put value X into register ELX. However, it doesn't really change the stack. And this address here, it's the value is still X. No one changed that. So that is how it works. Then we have the complicated instruction, which is call. Call instruction can take different parameters. It can be a register, it can be a number. When it is a register, this is actually called an indirect call. If it's a fixed number, that's called a direct call. As you can see that when we do what we discussed earlier in this class, recursive disassembly. We follow the control flow, and the target of this call is where the control flow goes. Right? So some static analysis tools will try to infer what is the target of call. However, if the target of the call is some type of register, it's very hard to infer because technically only one time when you reach here, you know what the target, right? So in this example, let's say, so this part is code. This is no address. This is high address. The code goes this way. The stack also goes this way, but this is high address. This is no address. So the code here is we have push one already executed. Now ESP, the instruction pointer, points to call EAX. Now after this instruction, there is a pop instruction. Okay? And then the ESP right now points to X. So what happens after this is we will call EAX. So the instruction, call instruction will be two things. The first, it will push the address of the next instruction onto the stack because it will send this address is a return address after call. After the call is executed, it's supposed to execute this. So the call will go to something. After that, it will continuously execute here. That's why we'll push this address onto the stack. So after we execute it, then it will move the destination address, which is inside EAX, into EIP. Okay? So what happens here is after we do this call, the address of this instruction will be pushed on the stack. What is interesting here is a lot of operations, they are implied in this instruction. Only looking at this instruction, call EAX, you cannot really tell the EIP is changed, the ESP is also changed, right? You don't know that, but they are actually changed. They are implied. So this is how you make a function call on this architecture. So if there is call, then obviously there should be return. And the return instruction is simple. It doesn't take some arguments. I think actually there is a version of the return instruction take a number of the arguments to balance the stack. But for most cases, it's just a return or return only, I believe, just a return. So what this instruction does, it also implies a lot of things. It will utilize ESP, but ESP is not showing this instruction. So this instruction will pop the top of the stack to EIP. So the top of the stack is what the ESP points to. Okay? It doesn't care what is the value of ESP. It will just pop wherever ESP points to EIP. That's it. So let's say this is a stack right now. We have Z, Y, X. ESP points here, and this is the code. We already popped something, then we have a return. Now we execute this return instruction. What happens is the value X will get into EIP. Okay. So the return instruction is equivalent to something, semantically, it is equivalent to something like pulp percentage sign EIP, right? It's equivalent. However, in Intel architecture, there's no instruction like that. There's no instruction pulp percentage sign EIP. In the Intel architecture, you cannot directly pulp things into EIP. You have to use this return instruction. So this is different for different architecture. I think maybe 64 version actually you can do that. And ARM you can definitely do that. Actually, that's what we do in ARM. We directly pulp things into. But in ARM, it's not called EIP, it's called PC, program counter. The same idea. Then there is something called enter and leave. So enter is just equivalent. One enter instruction is equivalent to those three instructions. Because a software layer, the compiler always generates those three instructions at the beginning of a function. That's why later Intel just decide, let's create a new instruction, enter, which is equivalent to those. Right? So the first instruction is push EBP. Second one is move ESP to EBP. So push EBP means you save the value of EBP onto the stack. Remember, since it's saved, you can change it now. Now we move ESP to EBP. Now ESP technically points to the old EBP. Then you subtract some number from ESP. So this is the beginning of a lot of programs. This is what they do. Okay, this looks a little bit strange, but especially the sub part. Why would I do that subtraction? Actually, we do that to reserve some space for local variables. Let's say the beginning is like this. After enter, first the old EBP is stored at here. Then the new EBP points to the old EBP. Then the ESP points to here. So here you like the top of the stack. And this part is kind of like the scratch memory for this function. And they can reference everything here using EBP. For example, here, everything here would be EBP minus something, right? That's perfect for local variables. Local variables, you don't know their absolute address when you compile it. But if you always put them here, you have the relative address to the old EBP or the new EBP. So a local variable can always be referenced by EBP minus something, okay? And on top of this, those can be referenced by EBP plus something. And actually they're used for parameters. The leave instruction is obviously the opposite of enter. What the leave instruction does is just to move EBP to ESP. So restore the old EBP and just pop EBP there. So stack is like each function's scratch memory, and each function can allocate space for local variables on it. And those addresses, like I said, they cannot be fixed at compile time. So when we reference them, we use some registers like EBP, ESP. Some architecture even use EIP, the program counter to do it. So in x86, we say the function frame starts from where EBP points to and ends at where ESP points to. So between that is basically this function's scratch memory. In say there are many different calling conventions. The calling conventions basically determines how do we pass parameters, how do we store them, where do we store them, and who will store that. It is a caller store that, it's a callee store that. Do we put them in stack, on stack, or do we put them on registers? And in the most popular calling convention we use in 32-bit machine is called this say declare. In this calling convention, the caller, the previous example, we have main function, we have a func. The main function calls the function func. So main is the caller, func is the callee. So the caller will push the arguments onto the stack, and from the right to left order, if there are more than one arguments, one by one, push them onto stack. Then you will execute the call function. The call function obviously will push the address of the instruction after the call to the stack as well, and then move the destination to ELF. And the callee, it's callee's job to save the previous functions pointers, frame pointers. So this is like the standard. After we define the standards, each of us, we can design our own functions, and my function can call your function can call my function, right? Because we follow the standard. Of course, when you do your C programmer, you do not directly do it. Your compiler follows the standard, okay? So for a function, it obviously it can be a caller and a callee at the same time. A function will be called by other functions, so it's a callee, and also it will call other functions, so it's a caller. So when it's a callee, it has to decide at the beginning of the function what it does. So in this convention, it refers to pushes previous frame pointers on the stack, and previous frame pointer is the EBP or RBP. Then you will set up new frame pointer, which is move ESP to EBP. So EBP always points to the beginning of my function's frame. Right? That's why right now my function frame actually is where ESP is. Then I move that to EBP. Then I will create space for my local variables by doing subtract some value on ESP. Then also the calling you need to make sure the stack is consistent on return, which means if you subtract something to ESP, before you return, you should add those back to the ESP. And also we put the return values in the ELF register. So most of those are the same for 64-bit as well. Just extend to 64-bit register. Most of them are the same. So we already looked at this. This one also. Now let's take a look at let me see if I have animation. So let's look at this concrete example. The same 32-bit global local variable code. So this is the main function disassembly. This is func disassembly. And let's say the main function, we can say that. Let's first find out the call, right? So this is where the call is. This instruction calls the main function for the func save. And in this func save, it takes one argument. And in this convention, that argument should be on the stack. That's why before the call function, we have a push function, push instruction to call, to push that argument to the stack. If you remember, in our C code, we're actually doing func temp, argument is 10, which is a in hex. That's why we push 10 on the stack, then we call this.
This is what the main function does here.
Then after that, we will transfer the control into the pump, and you can see.
Okay.
So the very first instruction we're doing is push EBB. We save that to stack. We move ESP to EBB. Then we subtract 18 in hex ESP. So we reserve. How big is that? It should be 16 plus 8, right? 24 bytes, right? So we'll reserve 24 bytes for local variables. So in that function, we will call printf multiple times. Yeah, we're calling printf multiple times. And where's printf? So why the parameters are different? So function plus 1a, function plus 2e. Okay, I'm not sure why we have 4 cores here, or 4 cores here. We are only calling 3 functions here. What's going on here? Oh, here. So those 2 are the same, right? So those 2 probably are function the printf. So the other functions could be, this one probably is injected by the compiler. That's not the printf. But we still should have 3 printf. Okay, we can debug this later to find out what's going on. I think I didn't label this. The version I put here, I didn't label it. So probably this is another injected by the compiler. This is probably printf. This is printf. There should be a lot of printf.
Okay. I'm not sure what's going on. I can debug this later to tell you. Anyway,
In short, in this convention, this is one of the stack lookup 32-bit version. In any function, the EBP should point to the previous function's EBP. It is saved onto stack. Then anything lower than that is a local variable. Anything higher than that, first EBP plus 4 should be the return address. If it's a 84 version, should be EBP plus 8. Then EBP plus 8 in this case is argument 1 plus C is argument 2. So we look at instructions using those kind of addressing. We should be quickly figure out what they are actually doing. For example, if you say this, then let's save the EBP. If you say this, it's a positive, means it's higher, then that's getting arguments. If you say this, minus 8, negative 8, that means it's getting local variables. It's referencing local variables.
Several examples I have here.
First one is move EBP minus 8 to EAX. So what is that doing? Yeah, it's moving a local variable's value to EAX. Then what is EBP minus 24x? Since we're using EAX, here we're getting the address. So we're getting a local variable's address to EAX. Positive indexing EBP plus 8, that's the first argument. EBP plus C is 12. That is
getting a second argument, if there is a second argument, right? Some functions, they do not use EEP to address things, they use ESP, depends on the model. But I don't think in our examples we are going to see that a lot. Okay, here is another example, factorial. This is a single example. We only have main function and the fact function. Our main function checks how many arguments are given to this program. It has to be true. The first argument is the name of the binary. The second argument is actually what you want to give to the binary. Then we will print out the factorial of that number, which is calling this function fact. Because whatever you give, there is a string. So we need to use a to I to change that string from ASCII to integer. A to I is a libc function, but I don't think I think it's not a standard libc function. Most of recent libc libraries, they probably do not have this function. You have some architecture, we do not have this function, but you can use sprintf to do the same thing. So here we change the string to integer, then we call a fact function, and this function is just a recursive function. It will show you that at the beginning, it will show you in the calculating the factorial of which number, and it will show you the address of the argument. The argument, remember, this one is on stack, right? So this function will call itself. So the stack will keep going down, right? So the address of n should keep going down. It will say different address n and keep going down. Until you hit this one, you will return 1. I will have to return this. So we can run this function, run this program. So if I just run this, we only have one argument, and tells me we need to give more. So this is, I give it 5. So it will first say, hi, I'm calculating fact 5, and the address of the argument is here. Obviously, this is on stack, FF, and the number is 180. Last 3 digits, 180, and you can see it goes down 160, 120, 140, 120, right? So each function, the function actually has a stack frame of 20 bytes. Each time you use this 20 bytes, not 32 bytes, yeah, 20 impacts. So it will keep going down, going down. So if we do 50, the same thing, right? Keep going down. Each time it's 32 bytes. Any questions so far? Everyone's following? Good, you guys are smart. Okay, so here is another simple example. We said that this example, I'm trying to show you that the arguments, they are pushed on the stack from right to left. So first we push E, then we push C, C, E, A. That's how we push it. At least for the 32-bit version. What does this program do?
Oh, I hard coded it here, so doesn't matter. Yeah, I hard coded it here. So what we can do is we can do an object dump, obj dump this one. We are looking for the main function first. Seven. Let me check the code. So the main function will call this one. Looks like everything is optimized away here. Because I hard coded everything, so looks like it's optimized away. Anyway, we can check the FP function. So you can see FP function. The FP function is expecting 5 arguments, right? And this is 32-bit version, so all 5 arguments should be on stack. So the first argument will be this version actually they're using ESP instead of using EBP. But the address would be so here. This function we didn't even save the EBP here because this is such a short function. So the ESP points to what? At this point, at the very beginning, ESP points to the return address, right? Because the previous function calls this function, so ESP points to the return address. So ESP plus 4 should be the first argument. So we find ESP plus 4 here. Then we have ESP plus 8, the second, say 10, 14. So those are the 5 arguments. So the order here doesn't really matter. If you switch those two, it's the same, right? So they just the compiler just decided to move the second argument to EAX first, then add it, but they're actually the same thing. So this is a 32-bit version. So in the homework, actually you will take a look at a different coding convention called fast call. And in the 32-bit, in fast call, in the regular coding convention, we are using stack to pass arguments. So there will be push, there will be pop, moving things from register to memory, and move things to memory from memory to register. It will reverse because memory is not part of the CPU. So that's why there are other coding conventions to make things a little bit faster. Faster call is one of those. So faster call will not put the first argument onto the stack. Instead, we will put the first argument in ECX and put the second argument in EBX. So in homework, you are going to read that disassembly to check out that. Even though on 32-bit version of x86, this is called fast call. This is actually standard for other architectures. For example, for 64-bit of Intel, this is standard. The first 6 arguments are using registers. Only the 7th we started using stack because there are so many registers available, and also on other architecture ARM needs those RISC architectures. We have so many registers, so we just try to use a register instead of memory, and it will be much faster. So, like I said, in 64-bit Intel, we do not use the stack to pass those arguments. The first register goes to RDI, second register goes to RSI, So we have so many registers. Those are new registers. R8, R9, they are not there for 32 bits. So if you have more arguments, then we will use stack.
So we are going to look at the same program FP, but we will look at the 64-bit version.
It's here. So keep on back, can you see that? Okay, so this is the same function. 64-bit, 32-bit.
We saw that they were using stack, even though they are using
ESP-based addressing. But here, for 64-bit, we're directly using those registers. RDI, RSI. So the whole function will only use the memory once. Other instructions were not even using the memory. Why do we need to use the memory here? Interesting. So you see, the last instruction is actually adding RDI to R8. So this instruction not really using the register. We're not really using memory. So this is no effective address. So basically it's adding this one to this one and put the value back to AX. The other way we can do it, we can use AND, then we'll move. So to save some space, to just use the one RDA instruction. So there's no memory access actually. This one doesn't access memory. So this function, no memory access, super fast
compared to the previous 32-bit implementation, we access memory many times.
Access memory is significantly slower than accessing obviously
Just inside of the CPU. Of course, there is another thing, cache, CPU cache.
that also plays a very important role, also in security.
I do some cache-based attack before on ARM architecture, and all those are related. Okay, just to remind you, 64-bit version, we have many more registers
From R8 to R15 and
8 more general registers. This one we already took a look. Okay, now we are going to do our very first attack in this class. We are going to overwrite some local variables. In this attack, we're not trying to hijack the control flow. So this is just in some literature that calls data flow attack, data oriented attack, because we're not trying to hijack the control flow, but it can be very serious as well. Let's see. This is a program.
This is a victim program we have. There is a secret global variable secret in this program as a string, and we have a main function. The main function takes 2 arguments, the combine arguments, and it calls the variable function. The vol foo here, just trying to show you this is the variable function. The vol foo takes 2 arguments, both 4 bytes. One is an integer, another one is a pointer, both 4 bytes. They will be on stack. Then we have the first one, the input will always be 0. The second input will be whatever we give it to the program. Then there's a local variable j. Then there is The local variable j will be initialized to the value 0 at the beginning. Then there is a buffer, which is a 6 byte. Okay, this is very interesting here, the 6 bytes. You cannot really trust it at binary level after it compile is 60 bytes. At the C level, when you program this, you define it as 6 bytes. Right? But the compiler may add some padding there, do some alignment. So it's guaranteed to be 60 bytes, but probably bigger. Okay, so we don't really know how big this is in the binary. Then there's a vulnerable function called string copy. What we're going to do is we are going to copy whatever you input to the program to this buffer. Okay, so obviously your input could be longer than 6 bytes or whatever the binary reserved for that buffer. So what will happen? What will happen if our input is higher than, is longer than that? What? Yes, it will overwrite. So what will overwrite? We will first override the local variable j here, right? We will first override the local variable j. If there are more data, we're going to overwrite the return address. Then we're going to overwrite. We're going to override the save the EBP first. Then we're going to overwrite the return address. Then we're going to overwrite everything higher than that address. Okay. So when we override that return address, what will happen is if this function successfully return, it will return to whatever data we override to there. Okay. So that's what we're going to do next week. So this week, what we're going to do is we simply override the variable local variable j. Okay. So what this function does is it will check the value of j. If the value of j is 0, it will just output IP to the full. Otherwise, it will output the secret. Right? That's it. That's the program. So if someone developed this program and tell you that you should always only give 5 characters, if you follow that, this program will always tell you IP to the full, right? But if you give more than that, let's see what will happen. Choice overflow local. Overflow local. Okay, so this is the program. I just do 3 characters, 1 to 3. So it will be IP to the full. If I do 5 characters, the same. If I do 6, actually the same, which means even though at C level, I say it's 6 bytes, but probably it's bigger than that. If we do 7, okay. So we will give this a secret. So if we look at the binary code, it's a summary of this. Let's try to understand where's the problem. So this is a vulnerable function. The vulnerable function where push EBP, move ESP, EBP, the subtract 24. That's 24, subtract 24 there. Then we will move EBP plus 8 to EAX. So what is EBP plus 8? The second argument, right? The second argument is a string. So actually, it's the address of that string. So EAX right now, this line, EAX stores the address of whatever you input. In my case, I put a 1, 2, 3, 4, 5, 6. That's the address of that in EAX. Then move that address to a local variable, EBP minus 6, which is Okay, I think right now there's no local variable for that. Anyway, we keep going, then we subtract the ESP again, then we push the EBP plus C, which is the third argument. That's for environment. That's for this is root. Oh, this one is wrong. Sorry. So EBP plus 8 is the second variable. In this case, it's a string because it's literally the same thing. That's the same thing. Then with EBP minus 12. So now we're going to make a function call, and this function call is string copy. Right? So string copy, how many arguments are there? 2 arguments. So right when you push 2 arguments for string copy, so string copy is this. So we can find the 2 pushes. This is the last push. This corresponds to the first argument. This is the first push, corresponds to the second argument. So that's why if you check ELX, what is ELX? So if we do kind of like a backward slicing algorithm in program analysis, you know that ELX is buffer, right? So you can check where is ELX. ELX is actually EBP minus 12. That's where the buffer ELX is. Then where is P? P is this time. P is EBP plus C. Let's say why is EBP plus C? Return is plus 4. Oh yeah, return is plus 4. First argument is plus 8, so plus 3 the second argument. Right? That's why EBP. This one is basically P, the second argument. This one is local variable buffer. So here we're calling a string copy. Also interesting is you see the instruction. This one is not telling you we're calling a string copy. Instead, it looks like calling something weird. That's related to that lazy binding important. Okay. Because right now we don't know why we don't know the answers. Okay. After that, there will be buffer overflow. There can be buffer. So let's check this. Let's this is return address on stack. This is saved EBP. Right? Then we know where the buffer is. Let's say this is the buffer. And buffer is EBP minus 12. Okay? So between the buffer and the saved EBP, we have 18 bytes. Okay, so where is the local variable J? Because there will be a compare somewhere, right? Here, we're comparing 0 to EBP minus C. So EBP minus C is that local variable J. Okay. EBP minus C. C is what? 12. 12 is actually 18. Okay. So actually in this case, the buffer is exactly 6 bytes, what we asked for. Okay. Right? So that's why when we input, so now we think, when we input 1, 2, 3, what will happen is we will write 3 bytes here, 1, 2, 3. Okay. So this J will still be 0. We will not overwrite it. But if we write 1, 2, 3, 4, 5, 6, what will happen? We will overwrite all those 6 bytes. So 6 there is a 0 after this, right? Okay. So we will not overwrite this. Okay. However, if we do 1, 2, 3, 4, 5, 6, 7, or you don't have to do 7, anything here. It will override this byte. Well, actually there are 4 bytes. You will override the least significant byte of J and causes an overflow. You're not supposed to write J. And because of that, we are going to print out this printing secret. This is how this works. So you can do anything here. Doesn't matter. It will override that byte and cause the overflow. So you can see that the problem here is the function string copy is not safe. The function string copy, you're not supposed to use it anymore. This one, we're just copy whatever you give to the destination. It doesn't check if the destination has enough space for that. If you are a C programmer, this is probably you can implement the string copy function. Very simple. Of course, if you write a C program like this, letters that I developed it, keyword here I want to review talk about people doing bad coding. Use example of this. They say this is bad coding. You should write C code like this. So this is much shorter. The interesting thing is if you're compiling, the compiler will generate the same thing. Who knows? The compiler is smart. It may generate the same thing. Anyway, that's why right now you're not supposed to use string copy. There are safer version of string copy. There are string uncopy. So all the string functions, there is a secure version, n, right? Which you have to specify how many bytes you want to copy it. So this actually have a animation here. This is inside the function, vulnerable function. At the very beginning, we have the address of P. And at the bottom of the stack, we have 0 of the first argument. Then we have return address. So now we push EBP. So this is actually after the red box. If we will push EBP, then we move ESP to EBP. So now the move ESP to EBP. Yeah. Now both. So before this, the EBP points to somewhere high, right? That's an old functions frame. But we'll push that here. Then we move ESP to EBP. So both ESP and EBP were pointed to the same address now. Then we subtract 24 bytes. Then we move EBP plus 8 to EAX. So now EAX will have the value 0 because we're moving that first argument from stack to EAX. Then we are moving EAX to that local variable J, which is at EBP minus C. And after that, the local variable J will also have the value 0. Then we subtract 8 to ESP again. But this instruction, at least so far, we're not really using it. Because of the addressing we're using EBP, we're not using ESP, so it doesn't really matter. Then we are going to push the EBP plus C, which is P, the second argument. So we're going to push it here again. Okay. And now ESP points to here. The P we're storing here again. Then we load effective address EBP minus 12 to EAX. Now EAX points to the local variable, which we know is the buffer's address. Then we push EAX. So push EAX. So EAX will be here. Okay. So here we are setting up the parameters, the arguments
for string copy. Right now we're setting up the parameter for string copy. So here, those are the two arguments for string copy. Then we call this string copy. After string copy, this part will be changed. And sometimes, unfortunately, memory higher than this will also be changed. Then after this, yeah, for example, we change that. We can actually change everything here. Okay, but as a attacker, you have to be very careful because your goal is not to crash the program. If you just make it very long, you can easily crash the program. But that's not your goal. Your goal is probably take control of the program. Let's say we make it very long, the program will crash. There will be a segment fault. No. The reason is eventually we change this and this. Okay. And when we return, we are going to jump to some address. What I put there? I put 4, right? So somehow we will jump to address 4, what is it? 4 in X. Okay. Anyway, something like that. Yeah, I don't remember. Anyway, it will treat that address. It will treat those 4. So 4 bytes of 4 in ASCII was a return address. Then obviously we probably don't have any value instruction here. Maybe that's an area region we do not have a privilege to access. So the program will crash. And also, even if we don't override that, we only override this, the program eventually will also crash. Because when we override this, when this function returns, we will use the old function's stack frame. And that stack frame will have the same architecture. It will have a return address. So eventually, it will lead us to something, some weird address. Okay, to show you that, we can do, let's say, how many bytes we have to do. So this is, so here is 18. So, yeah, here is 18 bytes. So if we overwrite 18 characters, the program will not crash. It will just give us a secret. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. That's 18 bytes. Okay, we're going to fully override this part, but now let's save the EBP. So this should not crash the program. Okay, maybe one byte off. Let's try 7. Okay, 7 should not override the program, but why 18? The under 0, but the under 0 should not be copied. Oh, the under 0 will be copied. Oh yeah. So actually, when we write 17 bytes here, so our input is 17, but actually the string copy will copy 18. It will append a 0 at the end, right? That's why when we do this, we overwrite 1 byte into the EBP. We make the least significant byte 0, and that is good enough to crash the program. We don't have to override more, just for 1 byte crash the program. So as an attacker, a lot of things we're doing in this semester is to carefully calculate how many bytes you want to override and what exactly you want to override there to achieve your goal. Usually your goal is not to crash the program. Okay, then let's say after that, we're adding 16 bytes to ESP. So ESP will move back a little bit because previously we were setting up the parameters for string copy. Now we don't need string copy anymore. We are going to balance the stack. That's what we're doing. Then we compare 0 with a local variable. That's basically how it works. Okay, so to defend this attack, any ideas? How do we defend this? What?
stack cookies. Stack cookies is a standard way to do this. Yeah, that's what we basically stack cookies is what we're going to talk about later. So what stack cookies does? I'm trying to think if stack cookies, the standard stack cookies can protect this. Actually, I think it cannot. Okay. So standard stack cookies, what we do is we will put several bytes lower here, lower than say the EBP. Okay. So we will put some random value here, but that random value is securely stored somewhere else. So when we return, we will compare that random value. If it is still intact, we check the integrity. If it is overwritten, we'll assume everything has been overwritten. So we think there's an attack. But the problem is a standard stack could be put in here. The local variables will be lower, right? So it's not good enough to protect that. Yes, we were protect the overflow to a return address, everything above, but not good enough to protect the local variables. Yeah. Of course, you can say, why don't we put the stack cookies somewhere here instead of here? Then, first of all, you don't know which local variable is vulnerable. In this case, buffer is vulnerable, but the static analysis probably don't know that. So what you can do is you put a stack cookie next to each local variable. Right? That's a solution. Okay. Another solution is you see the old compilers, the compilers I'm showing you, is moving. Okay. When we first define the local variable j, then that local variable j has a higher address. Then we define local variable buffer. Buffer has a lower address. And this attack obviously relies on that sequence. If j has a lower address than buffer, the buffer cannot overflow j. Buffer can overflow other things, but cannot overflow j. So there is another approach. I think it's quite standard right now. At least several compilers support that. Is they can randomize the order of local variables. Yeah, that's our approach. Okay, this is a 64-bit version of the same program. Let's say, let me see if I have animation. Okay, I don't have an animation here. Okay, this is a same program. The first thing you try to look for is I look for the function call. I look for the function string copy, and oh, this one. We have it resolved here. So this is string copy, and then we look for the arguments. The arguments here will be registers. So that's one. So here, those are registers. We're not doing it on stack. Then copy. So where is the so which one is this? Is which one is the first register? RDI. Right? I think RDI is the first one. Yeah, RDI is the first argument. The RSI is the second argument. So that's why here we're setting up RDI. Here we're setting up RSI. So RDI is RAI, RAX. RAX is RBP minus 8. Okay, so this stack is a little bit different from the previous stack. So this stack is the buffer. The buffer is at RBP minus 8. There we have RBP minus 12. So it's much closer in this case. So RDX is RBP minus 20. That's because previously we already set up that. Okay. So let's do this one. Let's check out how many bytes we need to override, crash the code. So we have our return address. Remember, this time is 8 bytes. Then we have saved RBP. which is another 8 bytes. Okay. Now after that, we have here buffer. Buffer address is RBP minus 8, which is 10. Okay. Then where is the local variable J? Which one is the local variable J? Here. RBP minus 4. Okay. So local variable J is at RBP minus 4. Interesting. You know, so this is an integer. So the J is here 32 bytes. It's not 64 bytes here. Okay. This is J. Right? So for this one, so this one, the distance between buffer to J is bigger than 6 bytes. Right? Or exactly the same bytes. The same. Okay. So it's the same. So this one, the 64-bit version will be the same. Is it the same? Why there's already the same? Oh yeah. It's because when we do this, we put 0 here. So then we change it. Right. When we put 6 characters, then we put another 0 here, but original everything here is already 0. So we need 7. Yeah, that's the same. Make sense? Okay. Let's keep moving. Oh, here you can see the loop instruction. For this function, we compare generate leaf. It's interesting. At the beginning, it doesn't generate enter. It generates those 3 instructions. Then generate enter. However, when at the end, we generate leaf instead of those 2 instructions. Okay. What's our time? The class ends at 7:40, right? 7:40, 7:50. Okay. 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 Then we have time to look at a lot of example. It's actually very similar, but a little bit more difficult. Okay. The main function is the same. We have a local variable J, a buffer. We use a string copy to overflow the buffer. However, the input, the J has to match this value for us to trigger the program to generate to output secret box. So what we need to do is we need to calculate how much bytes we should overwrite. Also, I give you a little trick here. We can use Python C. I think this is Python 2. Python 3, the syntax may be a little bit different. So this one will basically generate whatever you want, and you will feed that into the program. The reason we need this is a lot of inputs you are giving to the program will not be readable. They're not asking, right? It's not like always 1, 2, 3, 4, 5. So some actually is not asked. That's why you have to use a program to generally to feed in that. And this one obviously, this doesn't correspond to some readable ASCII. So to do this one, let's see.
So just give some random input. Either we're crash the program and R goes not to crash the program or goes to give us that this is a secret string. So several ways to do this. One way is to carefully disassemble this program. Find out how many bytes exactly you need to overwrite between here to here, so you can overwrite exactly that local variable. Another way, maybe simpler or automatic way, is to just guess. Right? I put those bad bytes there. Let me. Okay, so our input will be 1, 2, 3, 4, 5, 6, 7, 8. Okay, is the order correct? So the 1, 2 is lower. The order is not correct, right? Because this is a legal order. I will need to flip it, right? Yeah, we need to flip it. Yeah. So it should be this one. Yes. 5, 6, 3, 4, 1, 2, and this. Okay. So obviously this is not good enough to. Oh, yeah. So this is obviously not good enough. Then we can add maybe just add an A here. Still not good enough. And another one. So now we have how many bytes? Good. We need at least 6 bytes here. So this way. Oh, exactly 6 bytes. Right. So in this case, we didn't disassemble this. We do not really know the exact location it is, but we can guess. And this is very important because a lot of automatic tools is based on guessing. Because exactly you want to do program analysis on those will be very difficult. So a lot of times just guessing, buzzing. This is how we can practice. Okay, so this is actually it for this week. There will be this week there will be a lot of homework because we discussed so many things in this time. So there will be homework to replicate what I did in the class. There's homework to learn the lazy binding, also simple crack me to practice. But the simple crack me, you don't have source code. You have to do disassembly to understand the draw. Usually what I do is draw stack like this, try to understand, to calculate things accurately. Next week, we're going to study buffer overflow. Override requirements, and also we're going to inject some share code there. And there are many different places we can inject the share code. Also, so override this, return this. We will also override this, the EVP. Okay, so many ways to attempt. Okay, any questions? Okay, good. See you guys next week.